We're now going to look at the basic concepts of chemical bonding. So there are a couple different types of chemical bonds. Ionic bond is the pure electrostatic attraction between positive and negative ions. This positive and negative ions we get from ionic compounds when we have metals combined with nonmetals. When we have nonmetals combined with nonmetals, we end up with a shared electron bond. This is called a covalent bond. So we have a pair or two or three pairs of electrons that are in the space between the atoms, shared by both atoms, and this is what holds the two nuclei together. And we also have metallic bonds. And metals in solids will have a number of surrounding metal atoms, but these atoms together have a valence energy level for electrons, where electrons can travel freely throughout the metal. This is what gives the metal its electrical conductivity. So when we look at chemical bonds, we can describe a chemical bond by the bond energy. That's the energy required to break a bond. And when we break things, we usually do it in the gas phase, so we can isolate that one bond from everything else. So bond energy is the energy required to break a bond in the gas phase. Bond length would be the average distance between the two nuclei of the bonding atoms. This distance is not a static distance. The molecules are vibrating. But we're doing the average distance between the two nuclei. That would be at its minimum energy. And this is a balance between the attractive electron nucleus force and the repulsive electron repulsion, or nucleus repulsion. For most compounds, when they bond, they gain, lose, or share electrons until they have an octet of 8 electrons, 8 valence electrons around the atom. For ionic compounds, we transfer the electron completely from the metal to the nonmetal. So those electrons are no longer counted by the metal, and they're just counted by the new atom, the nonmetal. For covalent compounds, they're sharing the electrons, so we're going to count those electrons by both atoms. And the standard octet is going to be a completely full S and P sublevels. So S holds 2 electrons, P holds 6. So add them together, and that is the 8 electrons for the octet. Atoms such as hydrogen, beryllium, lithium, these atoms are near helium. Helium is stable with only 2 valence electrons, but it's still a noble gas, still extremely stable. So hydrogen only goes for 2 valence electrons, along with beryllium and lithium. They lose electrons to end up with only 2 valence electrons. We're going to start off describing these bonds using Lewis dot symbols. Lewis dot symbols, Lewis symbols, electron dot symbols. So what we're going to do is show the atom by using its symbol, and we're going to show valence electrons by using dots. And generally there's going to be only a maximum of 8 dots around the atom. We will find exceptions, but majority of compounds are limited to the octet rule. Ionic compounds, they transfer electrons completely from the metal to form a positive cation, and the nonmetal receives those electrons to form a negative anion. These compounds are very stable compounds. They have very high melting points, very high boiling points. They tend to be crystalline with very high structure, and they tend to be brittle, meaning if we hit them, they shatter instead of bending. For ionic compounds, we can describe the lattice energy. Lattice energy is the energy required to disassociate the solid ionic compound into gas phase cations and anions. So we can write this lattice energy as a series of steps of named reactions. So we're going to learn these named reactions. We're going to recognize the enthalpy of the reactions, whether they are endothermic or exothermic. We're going to learn how to add equations and energies up. This is Hess's law. And we're also going to learn to predict relative magnitudes of the lattice energy. So the lattice energy is the energy required to separate the solid ionic compound into gas phase ions. The solid ionic compound is very stable. So this is a very endothermic process to rip apart these stable ionic compounds into gas phase ions. So being endothermic means that our enthalpies will be positive. The lattice energy can be described by a version of Coulomb's law, where lattice energy is equal to constant times the two charges, the magnitudes of the two charges, Q1, Q2, divided by the distance between the two charges. So that means as the two charges get larger, the lattice energy will get larger. As the distance gets smaller, the lattice energy will get larger. So this equation tells us the expected changes in lattice energy with respect to charge or ionic size. So our lattice energy is going to get larger as we increase charge, go from +1 -1 to +2 -2, or +3 -3. So as we increase charge, our lattice energy gets larger. And when we have smaller diameter ions, we're going to have increased lattice energy. So we can get the relative lattice energy by looking at the compounds and deciding first on charge and then on radius. So if we compare lithium fluoride to lithium iodide, we have +1 -1 for both compounds. So the charge is the same. Lithium is identical on both, so we just have to look at the radius of fluorine and iodine. Fluorine being higher on the periodic table than iodine will mean that fluorine is smaller. The smaller radius of fluorine will mean that lithium fluoride will have a higher lattice energy. Same with lithium chloride, cesium chloride. We have a +1 -1, so the charges are the same. Chloride is the same, so we just compare lithium and cesium. Lithium is higher on the periodic table, meaning smaller radius, meaning higher lattice energy. So lithium chloride will have a higher lattice energy. When I compare magnesium chloride to sodium chloride, chloride is the same in both. Magnesium has a higher charge, it's +2 compared to sodium, which is +1. So the higher charge will make this a stronger lattice energy. So magnesium chloride will have a higher lattice energy than the sodium chloride. Comparing magnesium oxide with magnesium chloride, magnesium is the same on both. But oxygen has a -2 charge, chlorine has a -1 charge. So the higher charge on the oxygen will mean the magnesium oxide has a higher lattice energy. So some more compounds with lattice energy. Scandium nitride, a +3 -3, has a very high lattice energy of 7,547 kilojoules per mole. So for magnesium oxide, calcium oxide, strontium oxide, they're both +2 -2. They're all in the range of 3,000 and some kilojoules per mole. Lower than the +3 -3, higher than a +2 -1 down below. So for these three compounds, we go based on size. Magnesium is smaller than calcium, which is smaller than strontium. So magnesium oxide has the higher of the three lattice energies, and lattice energy decreases from there. Magnesium chloride, strontium chloride, we have a +2 -1 for both of those. We're now down in the 2,000 kilojoules per mole range. Magnesium is smaller than strontium, so magnesium chloride has a higher lattice energy than strontium chloride. Then we go down to the +1 -1. These are 1,000 or less kilojoules per mole. And we see the smallest cation, lithium, with the smallest anion, fluoride, has the highest lattice energy. We go down to the bottom, we have the biggest cation, cesium, with the biggest anion, iodine. This has the smallest lattice energy. So lattice energy decreases as our ions get bigger.